Welcome back. In the second part of polar and nonpolar molecules, I'd like to say a few words now about the polarity of organic molecules. Organic compounds are most compounds containing carbon. We say most because we don't consider carbon monoxide, carbon dioxide, and carbonates to be organic. But an overwhelming majority of compounds containing carbon are considered organic. We give organic compounds special consideration because there are more organic compounds in the world than any other type. Here are just 3 examples. Notice how they all contain carbon. Also, notice they are quite large compared to the other molecules we've seen. For this reason, it makes it difficult to sketch the shape in order to assess the polarity. Luckily, we can apply some shortcuts. First, know that most large molecules, like what you see here, are at least slightly polar. After all, to be nonpolar, it needs to be perfectly symmetric, and the larger you get, with a variety of elements and shapes possible, that becomes less and less likely. Second, for organic compounds, many of which are large, we're mostly interested in what region of the molecule is polar and what region is nonpolar. Let me show you what I mean. Consider the organic compound butyric acid. The key is to notice the 2 distinct regions of this molecule. First, we have this side of the molecule. We refer to this as a hydrocarbon region. Hydrocarbon means containing only carbon and hydrogen. Second, we have the rest of the molecule. This is the non-hydrocarbon region, which includes every part of the molecule that's not just carbon and hydrogen. Once you identify the hydrocarbon and non-hydrocarbon regions, then just remember this. 1. Hydrocarbon regions are nonpolar, and 2. Non-hydrocarbon regions are generally polar or ionic. Why is that? Here's the shape of butyric acid if we were to sketch it out. The hydrocarbon region, with only carbons and hydrogens, is nonpolar because the carbon and hydrogen bonds aren't very polar to begin with. After all, their electronegativity difference is quite small. Carbon's electronegativity is 2.5 and hydrogen's is 2.1. So the bond is polarized, but so little that we don't even bother writing in the partial charges. Further, the carbon and hydrogen bonds are arranged in a manner that's very symmetrical. Bottom line, it makes that part of the molecule nonpolar. The non-hydrocarbon region is polar because the bonds themselves tend to be more polar. For example, there's a big electronegativity difference between hydrogen and oxygen. 2.1 for the moderately electronegative hydrogen and 3.5 for the very electronegative oxygen. Further, these bonds are oriented in a less symmetrical way because of the impact of the unshared pairs of electrons on the geometry. And if that explanation isn't perfectly clear, the good news is you generally don't have to dig that deep to determine the polarity of an organic molecule. Simply remember, hydrocarbon regions are nonpolar and non-hydrocarbon regions are polar. See if you can apply that to the next problem. Consider vitamin A, shown here. Identify which part of the molecule is polar and which is nonpolar. Remember, you don't need to redraw the molecule at all. Just circle which parts of the molecule are polar and which are nonpolar. Stop the video now. The large section with only carbon and hydrogen is nonpolar, and the very small region with the OH group is polar. Now technically, overall, vitamin A is slightly polar. After all, to be completely nonpolar, a molecule needs to be completely symmetric. However, since its nonpolar region is so large, its properties are much more like a nonpolar compound. This has far-reaching implications. For example, vitamin A is classified as a fat-soluble vitamin and not a water-soluble one. Water-soluble vitamins, like vitamin C, now shown on the screen, are much more polar with multiple polar regions, which, as we'll learn in a later chapter, are molecules that mix well with water, which is also polar. One more question before we wrap up this brief lesson. Phospholipids play a critical role in biological membranes, and the way they contribute has everything to do with which end of the molecule is polar and which is nonpolar. The structure of one such phospholipid is shown here. Identify the region of the molecule that is the most nonpolar. Stop the video now. The long hydrocarbon chain is the nonpolar region, and the other end is the polar end. It even has some ionic character with the formal charges on the nitrogen and the oxygen. In cell membranes, it's the polar end of the phospholipid that is oriented toward wherever water is, because both are polar, and polar interacts well with polar. Much more about that in biology. Okay, remember those balloon demos we saw at the outset of the polar and nonpolar molecules lesson part 1? Well, when you electrostatically charge a balloon by rubbing it on your hair, electrons get transferred from your hair to the balloon, giving the surface of the balloon a temporary negative charge. Well, since water is polar, as we saw in part 1, the positive ends of the water molecule are attracted to the negative balloon and are drawn toward it. Hexane, on the other hand, is just a hydrocarbon, C6H14, and it's only a hydrocarbon. That means it's completely or nearly completely nonpolar and has no negative or positive end, and therefore can't be attracted to the balloon. Well, thanks for listening, and see you next time.